In this presentation, we have to talk about the transmission coefficient. This is a continuation of the null effect. In the case of transmission probability, in the case of transmission coefficient, it provides the probability of transition of the particle through the barrier without reflection. The transmission coefficient is given by transmitted probability density current divided by incident probability density current. Here the transmitted wave is represented by f into e power I k max by the way of taking the complex conjugate of that wave function and is multiplied by v. We have had the value of transmitted probability density current. Then the incident probability density current is v into a star of e power minus I k x into a into e power I k x. So we have had v a star. In the numerator we have had v f star. So we can cancel the term v. Finally, we arrived at f star divided by a star because the transmitted wave is f into e power I k x. That is phi 3 of x. If you find out the value of f star, the value is 1. So we have returned the value of f star as 1. Then a star is calculated in the previous case also. The value is cos h square k2a plus 1 by 4 k2 by k1 minus k1 by k2 whole square sin h square k2a. Now we should modify this equation in the required form. For that, this is written as T equal to 1 divided by cos h square of k2a plus k2 square minus k1 square whole divided by, this is k1 k2, bring this 4 to the bracket, then 2 square 4. So 2 k1 k2 whole square into sin h square k2a. See this cos h square k2a is present as such, k2 square minus k1 square whole divided by k1 k2 whole square. Then this 4 goes to the bracket and this is taken as 2 square. So k2 square minus k1 square whole divided by 2 k1 k2 whole square. Then this is modified as 1 divided by 1 plus sin h square of k2a plus k2 square minus k1 square whole divided by 2 k1 k2 whole square into sin h square k2a. This is equal to 1 divided by 1 plus sin h square k2a into, take the sin h square k2a as a common term, 1 plus k2 square minus k1 square whole divided by 2 k1 k2 whole square. See this, I have taken out sin h square k2a outside. So the remaining term is 1 plus the entire term. k2 square minus k1 square divided by 2 k1 k2 whole square. Now we should simplify this term. This term should be simplified. 1 plus k2 square minus k1 square whole divided by 2 k1 k2 whole square is equal to, see, 1 plus k2 square minus k1 square whole square whole divided by 4 k1 square k2 square. This is equal to 4 k1 square k2 square plus a minus b whole square formula we have to apply. K2 power 4 plus k1 power 4 minus 2 k1 square k2 square. 4 divided by 4 k1 square k2 square. This is equal to 2 k1 square k2 square plus k1 power 4 plus k2 power 4, 4 divided by 4 k1 square k2 square. This is equal to k1 square plus k2 square whole square 4 divided by 4 k1 square k2 square. Now we should substitute this value in the modified form. This is further modified as k1 square plus k2 square divided by 2 k1 k2 whole square. So instead of this term we have to substitute and write. Transient probability t is equal to 1 divided by 1 plus sin h square k to a into the factor k1 square plus k2 square divided by 2 k1 k2 whole square. This is the value of t, transient probability. In this equation, we have to substitute the values of k1 square, k2 square, then the value of k1 square is equal to 2me by h cross square, then k2 square is equal to 2m by h cross square into v0 minus c. Therefore, k1 square plus k2 square equal to 2me by h cross square plus 2m v0 by h cross square minus 2me by h cross square. This is equal to 2m v0 by h cross square. Then k1 square plus k2 square whole square is equal to 4m square v0 square divided by h cross power 4. This we have calculated the value of k1 square plus k2 square. Say, we know the value of k1 square is equal to 2me by h cross square, k2 square is equal to 2m by h cross square into v0 minus e. Now I have calculated k1 square plus k2 square whole square. In order to find out this term, say, in order to find out this term, k1 square plus k2 square whole square is separately calculated. This is already known to you. K1 square k2 square values for m square v0 square h cross power 4, that is over. Then 2 k1 k2 square is equal to 4 k1 square k2 square. This is equal to 4 into k1 square k2 square. If you make the multiplication, you can get 16 m square e divided by h cross power 4 v0 minus c. So k1 square plus k2 square whole divided by 2 k1 k2 whole square is equal to this. I have substituted the value and then simplified. You can get v0 square divided by 4e into v0 minus c. This is this factor. Now, we should calculate the transition probability value T by substituting this value in the above equation. The value of T is equal to 1 divided by 1 plus this value k1 square plus k2 square divided by 2 k1 k2 whole square value is this v0 square divided by 4e into v0 minus e, then sin h square of k2 into a. The value of k2 square is 2m by h cross square into v0 minus e. So we have to calculate the value of k2. K2 is equal to 2m into v0 minus e inside the root divided by h cross out of root. So sin h square of 2m into v0 minus e inside the root by h cross. Without root we have to write h cross. Into outside root we have to write a. This is the value of transition probability. E equal to 1 divided by 1 plus v0 square divided by 4e v0 minus e into sin h square root of 2m into v0 minus e by h cross into a. This is the value of transition probability. This value not equal to 0 is meaningful, so that the particle is passing through the barrier without reflection. The probability of transition depends upon two factors. One is the height of the potential V0 and another one is the width of the barrier. Suppose the barrier height is too large and the width is also large, the transition probability is very less. So this is our tunnel effect. The tunnel effect points out the phenomenon of transmission of a particle through a potential barrier of finite width and height, even when its energy is less than the barrier height. It is called quantum mechanical tunneling. So there is no need for the particle to come back, even though the height of the barrier is greater than the energy of the particle. There is another probability for the particle to make its forward journey without reflection by the way of quantum tunneling. That's all about tunnel effect. Then we may provide a pictorial representation to explain the entire process. See, this is the pictorial representation of tunnel effect. Here the height of the barrier is V0, the width of the barrier is A. The incident particle is having energy E lesser than the height of the barrier. Psi 1, psi 2, psi 3 are the three regions. Then the probability of transition of the particle is represented the way of crossing the barrier. The particle is coming out lesser. So it is pointing out the incident at the different figure, the outcoming particle, the wave corresponding to the outcoming particle, which means that the amplitude is getting reduced. So the probability of transition is acceptable one. No need for the particle to reflect back. There is some probability for the particle to make its forward journey without reflection. This is called quantum mechanical tunneling. Thank you.